Hello, everyone. This is Professor Jeff Wilkerson at Luther College with an introduction to Exercise 12, Galactic Distances in the Hubble Lemaitre Law from Astronomers as Observers and Experimenters, published by Kendall Hunt. So what we're looking at in this exercise is the Hubble Lemaitre Law, and we want to, this is an important law for a lot of different reasons. Our focus in this exercise is largely the way this law would be most used today, which is to determine distances to galaxies. That's probably its most common use. Originally, when the law was first developed, Hubble figured this out, that if you plot the velocity of recession in, say, kilometers per second of a galaxy, most galaxies appear to be receding from us. Almost all galaxies, only the very nearest ones are not. The rest are receding from us. If you plot the velocity of recession in kilometers per second as a function of distance in megaparsecs, what's really critically important here is that relationship appears to be linear. You can fit a pretty good straight line through those data points. And as you fit the straight line through those data points, what that means is that's really consistent with our model that it's space itself that's expanding and pushing these galaxies apart from one another. If this galaxy is twice as far away from us as this galaxy, there's twice as much space between us and this galaxy as there is between us and this galaxy. And if that space that's there is expanding at the same rate, then this one should be moving twice as fast because it's got twice as much space pushing it away from us. And so this linear relationship is exactly what we would expect, and then becomes a critical piece of our understanding of the Big Bang theory and the development of the Big Bang model. And so this is really important work and really critical for cosmology in general. Not really what we're focused on in this exercise. What we're going to say is, okay, once you establish this relationship, you can determine the distance to some galaxy by measuring its recession velocity, and then come over here. It's best done with a cluster of galaxies, okay? All of this work is best done with a cluster of galaxies because if you think about that cluster of galaxies, you're out there, it's moving away from you this direction. Within that cluster, these galaxies are orbiting around the center of mass. Some of them are orbiting towards you, some of them are orbiting away from you. And so some of them are adding to the recessional velocity, some of them are subtracting from the recessional velocity, some of them are orbiting up this way and neither adding nor subtracting, and they may be not straight towards you, so they may have different amounts, and they may be closer to the center of mass of the cluster and all of this stuff. And so you want to average over as many of these galaxies in the cluster as you can to take out these effects to try to determine the recessional velocity of that cluster. You also need to know the distance independently of this velocity in order to make this graph. So I would recommend right now, you can go back and you look at the distances of Cepheid variable stars exercise, and you can look at the supernova 1987 exercise. Supernovae and Cepheid variable stars are just a couple of techniques that we would use, or plenty more, to measure the distances to these galaxies to determine this relationship. So this is what we got going on, and this is what you're going to do first of all. You're going to plot this. You'll see in table 12.1, I think it is. Yeah, table 12.1 right there. So you can see some measurements of distances to clusters of galaxies and some recessional velocities of those clusters of galaxies that you're going to use to make this plot. And you can make this plot on the graph paper that's right there in the lab, or you can do that on a computer or your own graph paper, or however you want to go about doing that. And so you want to make this plot of that data and build this relationship and measure the slope of that line. The slope of the line is going to be the rate of expansion of the universe, the so-called Hubble constant. Pick a point that's on the line, because these points are scattered around the line. It shouldn't come as a surprise to you that there's scatter in that data. These are hard measurements to make. We just talked about you have to average over a bunch of galaxies. People might choose different galaxies to average over. They might do different things in that way. And so you shouldn't be surprised that two different groups will measure the recession velocity and the distance to the same galaxy cluster and get different results that way. So you got the scatter here. Pick points that are actually on your linear fit, and you have the computer do it or you do it yourself, and put those points right there. And the rise over the run, delta y over delta x, delta v over delta d is going to be your slope. And you've got something that looks like this. The velocity of recession in kilometers per second is equal to something we call the Hubble constant times the distance. We put that sub-zero on the Hubble constant to remind us that that's as measured today. We do that in cosmology quite a bit. To say the word constant can have different meanings, believe it or not. And so it's constant in space, perhaps, but not constant in time, perhaps. And so that means as measured today, that's the Hubble constant. So the slope of that line is your Hubble constant. And that's going to be measured in kilometers per second per megaparsec. Okay, so that's your job. That's your first task in this exercise, is to go figure that out by making that plot. And then we're going to get some data from other galaxy clusters, and we're going to measure the distances to those galaxy clusters by measuring the recession velocity. If you have the recession velocity, if you measure a recession velocity right here, you can just drop down and get the distance, or better yet, just plug it into this equation, this relationship, and see what you have going on right there. So this is one of the things we want to, one of the learning outcomes for this exercise is going to be understanding how astronomers very commonly measure distances to galaxies and galaxy clusters, and to practice measuring redshifts as we've done in other exercise, and to practice our analysis techniques like this to get better at doing this kind of graphical analysis with data. These are just some of the learning outcomes that we associate with this, that I associate with this exercise, that are important outcomes to be working on. So it's important to think historically about the development. This is such a key piece of the Big Bang model, the history of the universe that we have developed, our understanding of the history of the universe, that this is an important, for that reason too, an important thing for us to be working on. So what you want to do is you want to measure the redshift of these galaxies. I recommend going back and looking at the evidence of the Earth's revolution lab right now to understand dispersion of spectra and thinking about the spectra measuring the redshifts like that. We're going to follow that technique from that lab in here. And if you don't go back and look at it, that's okay. It just might make it a little bit easier for you to work on this. What you're measuring is how far to the right, how far redshifted these two dark, I don't know if you can see them on this video, but you surely can see them on the book that's there in front of you. Those two dark lines, those absorption lines, a couple of calcium lines. In particular, notice that the tip of that arrow points to the rightmost of those lines, the right of two of those lines right there. We can't really tell where these start, so my recommendation is just to measure the length of that arrow. Use your trusty digital calipers if you have them, and measure how long that arrow is across there. So if you can measure that arrow, and then you get the length of that arrow on this picture. But that's not all the information that you need, because this picture we could have made any size we wanted to. We could have turned the page horizontally and blown the picture up so that it was longer across here, or we could have shrunk this down and you would have different arrow sizes. You need to convert that to an actual change of wavelength, a delta lambda, because you're going to say V over C is equal to delta lambda over lambda, your Doppler equation that you've used probably before. That's a simplified version of the Doppler equation. When some of these redshifts are big enough, you might not be able to get away with using that simplified version, but that's a discussion for another time. That's a bias that's going to be built into this data, an uncertainty that would be built into this data. So one good way to do this, you could measure the dispersion of the spectrum as we did in the evidence of the Earth's revolution lab, and do the calculation out that way. But another good way to do this work is to just ask the question, if this arrow represents the shift of the one line that we're looking at in there, the delta lambda of one of the lambdas that we're looking in there, we could say what fraction of the, if we want to set the scale for this, we could say what fraction of the separation between those two bright lines out on the end. You have a bright line out here and a bright line out here. How long is that arrow compared to the separation of those two lines? Because we can come down here to our finder chart and we say those two lines, one of them is 5,015 angstroms, one of them is 3,888 angstroms. So the separation of those two lines is 5015 minus 3888 angstroms. So we know if the arrow were the same length as those two lines, it would have a delta lambda. It would have a shift of 5015 minus 3888. If it's half of that, it would have half of that shift. And so we can take this measurement of the length of this arrow and divide by the separation of those two lines, and that tells us what fraction of 5015 minus 3888 is our delta lambda right there. And then we know the right of those two calcium lines the lambda is given to you in the exercise, so we know what the lambda is, and we can go in and we can measure this. Good to think about what your uncertainty is as you do this. I'm assuming you'll have a pretty hard time measuring the length of that little bitty line in the top picture. And so you might miss the length of that line by 20% or 30%. And that means presumably you'll miss, if your uncertainty is 30% in that, then your uncertainty is going to be 30% in that. And so it's good to think through all of these uncertainties as you go through. There's some uncertainty in the slope of your line up here as well. And there are certainly technical statistical ways to figure out the uncertainty of the slope of a line. Presumably, we're not wanting to do that in this exercise, but you could. And go in and figure out what this uncertainty in this slope is. But you could look to say, how big could this line be and still hit the data points? And how shallow could it be? How steep and how shallow could it be to hit those data points? And sort of estimate an uncertainty in your slope up that way. And then you can add those uncertainties, uncertainty in the length of your line, the uncertainty in there. You could add them in quadrature would be the appropriate way to do that. But you could also just say, whichever one's bigger, I'm going to call the dominant uncertainty. So by the time you get out to these long arrows, you should be able to measure the length of the arrow pretty well. And probably the uncertainty in your slope is your dominant uncertainty. These short arrows, particularly that first arrow, is so short that the uncertainty in measuring the length of the arrow probably swamps the uncertainty in this slope. So these are things to think about. Why is that important to think about? Well, these are things astronomers have to do all the time. They have to say, okay, suppose I found something interesting, and maybe that thing that's interesting, if this isn't a line, if this is curving out here, then we might have evidence that the universe is speeding up or slowing down. At great distances, we're looking back in time a long ways, and Hubble constant might be different, and we can say, okay, the universe has been speeding up, the universe has been slowing down, and we found evidence for dark energy, for example. And so or dark matter slowing down, whatever. But if it's speeding up as we think that it is, then we find evidence for this dark energy. And so we might want to know some deviations out there. But we only know if we've measured those deviations, if we know our uncertainties really well. If we know how uncertain is that velocity we just measured. Is it consistent with falling on that line, or is it not consistent with falling on that line? And that's the kind of things that astronomers have to work at, the kind of decisions they have to make, the kind of processing decisions they have to make and work on as they go through this. So this is a good exercise for thinking about some of those things. It's a great exercise, really important. This is as important a graph in the history of astronomy as, maybe not as important as the HR diagram, but there are a few graphs out there that are just really, really important that tell a story about the history of the human understanding of the universe and our place in the universe and the history of the universe and the evolution of the universe. And this is one of those graphs. So you just doing this exercise, just making that graph is really important. Being part of that process and understanding how humans understand the universe. So I hope you appreciate that and the significance of it and enjoy doing this exercise and think about how it is we know what we know about the history and the future of the universe. If you have any questions, contact me and let me know, and I'll see if I can answer some of those questions. Good luck with it, everybody.